Defluoridation refers to the removal of excess fluoride from drinking water. This is an important problem because it affects a large number of people who consume excess fluoride. I'll define what is excess in a short while. But it's also a difficult problem to solve because it tends to hit back. Work was done in collaboration with students and colleagues at IASc, except Professor Arup, who is at Lehigh University. Funding from DST and the Space Technology Cell are gratefully acknowledged. This is the outline of my talk. I will briefly describe what fluorosis is and then uh, mention how we try to remove this excess fluoride. Finally, I'll summarize. Fluorosis is a disease caused by ingestion of excess fluoride by people or animals. Here is how fluoride gets into the water. There are minerals such as fluorapatite in the Earth's crust. Leaching of these minerals leads to fluoride in groundwater especially. And then there are industrial effluents like this one. In India, mostly phosphate fertilizer industries. In some other countries, semiconductor processing industries will lead to discharge of fluoride bearing effluents. When plants are grown in this water, sorry, this presentation jumps a bit, I don't know why. They take up some of the fluoride. In particular, tea has high levels of fluoride. So if you're drinking tea, you might add a little bit of milk to it because the calcium in the milk tends to bind some of the fluoride and you'll be less affected. Fish also has the fluoride, vegetables, and so on. Here are some of the minerals: fluorapatite, fluoride, and cryolite. Don't worry about the formulae, but just to give you an idea of what minerals are there. In India, the major sources of ingestion are water and food. Dental products, most commonly used one is of course toothpaste, is not of so much concern except with small children who tend to swallow maybe up to 20% of the toothpaste. So there some fluoride goes in. Most of the brands available in the market contain 1000 ppm available fluoride. So that is to be taken note of. Now, the guideline limit for drinking water that is supposed to be relatively safe concentration is fixed by the World Health Organization as 1.5 milligram per liter. But the Indian standards is more conservative. It prescribes 1 milligram per liter as acceptable limit and 1.5 milligram per liter as permissible limit. In this talk, we will take 1 milligram per liter as a reference. Okay, just because the fluoride concentration is close to 1, we cannot eat, drink, and be merry. Because, as shown by this person who had fluorosis, he was advised dietary changes because he was consuming a lot of black tea, black rock salt, and so on. So, after this change, in about 6 months, there was an improvement in the level of fluoride in the blood. So, the engineers tend to overlook dietary interventions and focus on technical problems, technical solutions. But sometimes the doctors may also have a useful role to play. So the optimal intake of fluoride is said to be around 0.05 to 0.07 milligrams per kg of body mass per day. Optimum arises because some small amount of fluoride is believed to protect the teeth against dental caries. In some countries which are not affected by fluorosis, like USA, they add fluoride to water. This is a controversial topic, but I will not get into it right now, whether to add or not to add. Here's a example of dental fluorosis. It is shown by these brown bands on the teeth. Generally, dental fluorosis affects person during the stage when the permanent teeth are being formed. And this is a more severe case of skeletal fluorosis, where the bones become deformed and the person is unable to stand except with the aid of a stick. Here are countries affected by fluorosis. India is there prominently, along with the neighboring countries, parts of Africa, and Mexico, South America, Australia, and so on. In India, the newspapers highlight this problem, and this provided the impetus for me to switch to a completely different area. Here are some fluoride concentrations at a few places in India. Punjab and Rajasthan lead the way, but Karnataka is also there. And uh, these levels are very much above the acceptable limit of 1 milligram per liter. So in these places, it doesn't mean every place in say Jaipur has 18, only some places. So depending on where the person stays, he may or may not be consuming, he or she may not be consuming excess fluoride. Here is a poignant cry for help or show by a villager affected by fluorosis. This is more than what the scientific articles will tell you, just a more clear, a detached way. Here they say our shoulders, hips, and ankles are swollen all the time. If we squat on the floor, it's painful to stand up. So we wish we could do something to help people like this. That's the reason for so many people working on fluorosis. But there's a ray of hope. Here's a lady whose back has become bent because of fluorosis said after an NGO constructed rooftop rainwater harvesting and she started drinking the water, in about 6 months, the pain was eliminated, but the posture did not improve much. Fluorosis is incurable, but at least pain relief can be there if suitable solutions can be found. Defluoridation is, in a sense, an unending quest for solutions. Starting with the work of Prof in 1934, he said that nobody had proposed a method to remove this ion and proposed the use of aluminum sulfate, sodium aluminate, etc. as precipitants. In precipitation, two reactions in the liquid phase react to form an insoluble product which may settle down or float up. And also the use of zeolite, uh, silica gel, activated alumina as adsorbent. Adsorbent is one which is usually a solid, and some species, usually, say in our case fluoride, is transferred from the liquid phase to the solid phase and is bound by the adsorbent at active sites. After a while, all the active sites are used up and the adsorbent is said to be saturated. Either it has to be thrown away or regenerated. Now, in this talk, I will mention quite a bit about activated alumina. So, just keep this abbreviation in mind, AA. I will refer to it as just alumina for brevity. Now, the present state of affairs is like this. There are a large number of papers published on defluoridation, and if you just use the keywords I'm sorry, this point, yeah. Defluoridation and drinking and water and search in Web of Science will find about nearly 1,000 papers. But the actual number is several thousand because many papers don't use this word defluoridation but say removal of fluoride. So there are a large number of papers published. In fact, for some of them, there's a standard template and you can go through steps and do the same thing. If you're good at material chemistry, you can synthesize a new adsorbent and do the same steps all over again and publish one more paper. But the people susceptible to fluorosis is close to 200 million. This is a rough estimate. Now, these seem to be like parallel lines extending to infinity. So, why are they not meeting? And the reason may be that there is not enough work done to translate things developed in the lab to the field level and sustain it over a long period of time. By long, I mean, say 10, 20 years. As of now, there is no plant running in India for the past, say, 20 years, which has consistently removed fluoride and people are using that water. There are many solutions, but every solution leads to a problem. Emerson said, every sweet has its sour, every pleasure has its pain. Similarly, every solution seems to lead to a problem. Here's one of the early attempts from India by the National Environmental Engineering Research Institute at Nagpur. It's called the Nalgonda technique, named after a village in Andhra where the fluoride level was high. It involves use of alum and lime and adding to water. The alum, when it dissolves, it produces aluminum hydroxide flocks, and they will bind the fluoride and settle down. From an engineering viewpoint, you see different time scales are involved. Seconds for mixing, and flocks are insoluble particles, loosely bound particles. Minutes. Sedimentation of the flocks, hours. Finally, filtration to remove the flocks because we can't drink it with them, and then addition of bleaching powder to disinfect the water. These are the steps. So it seems simple, but the reaction is complicated. You don't have to, I don't know how they thought of this reaction, but the main thing is it forms some complex aluminum hydroxide fluorine compounds which settle down. The problems with this technique are that the dose of alum and lime depend on the alkalinity and the fluoride concentration. Throughout the talk, CF refers to the fluoride concentration, usually measured in milligrams per liter, and alkalinity is the ability of a water to neutralize an acid. So it usually consists of hydroxide, carbonate, bicarbonate ions concentrations. The high dose of alum, in some cases, it may lead to higher levels of sulfate than than prescribed by the Indian standards, which is 200 to 400 milligram per liter. If you have high sulfate, the taste may not be palatable to the consumers. And aluminium is limit also is only 0.03 to zero point 0.2 milligrams per liter. That point, zero point 0.2 is a guideline, but this is also controversial because there is many reports saying it may be linked to Alzheimer's disease, and other reports saying it is not linked. So we won't get into that. And finally, this method generates a large amount of sludge which has to be disposed of. Of course, if you have enough land and it's protected from rain or other water, then you can dispose it. But in India, everything is at a premium, space and vacant land and so on. So it is difficult. So this is an assessment nearly 30 years after the method was introduced. The author says it has not achieved much success in the field because it needs constant attention. Here is a comparison of different methods. Nalgonda I've already mentioned, but the attractive feature of this method which prompted the people to use it initially was the low cost, operating cost, not the capital cost, all this operating cost. Adsorption, which I mentioned, it requires periodic regeneration, otherwise you have to throw the adsorbent. Okay, the cost is order of 1 rupee a liter. GAC refers to granular activated carbon. A is activated alumina. Electrocoagulation, where you dip say aluminum electrodes into water and pass current, the aluminum anode dissolves and forms aluminum hydroxide flocks in situ, which bind the fluoride, and they will float up. Then after you switch off the current, they will settle down. You wait for a while. So this also, the cost is low, but a fair amount of sludge is generated. Reverse osmosis is another favored technique because it's standalone, but it requires electricity. And the bad thing is that it produces a reject stream, which is having a high concentration of fluoride, which and is a significant fraction of the feed. The cost at a community level plant at a village we visited at Yellampalli, the government was selling it at 10 paise per liter, which the villagers were happy to buy. Rainwater harvesting, there is no operating cost as such, but capital cost is involved in building a sump, and the dirt on the rooftop, including bird droppings, will come into the rainwater. One simple way to avoid this is to discard the first flush of rainwater. Of course, if it rains at night, you may not be awake, so you won't know when the first few batches are coming. So, but the villagers uh, here in the village in Yellampalli, they had funds only to build a sump to store about 4 to 5 months of rainwater. After that, they were back to the borewell with the high fluoride level. Solar distillation, again negligible operating cost. Sometimes in one place in Gujarat, what happened was a peacock started pecking at the glass plate, so it used to break now and then. So that is part of the operating cost. And the throughput, the main disadvantage is if it's cloudy, then you won't get enough water unless you have a large area. But this is a sustainable technology. In Chile, it was used for about 40 years to supply water to a coal mining, nitrate mining town. Rainwater harvesting is underrated by engineers because it's nothing to it. No, it's low tech. But the thing to note is that when the water is stored in the sump, it may have bacterial contamination. Here is one example where the fluoride concentration is well below the acceptable limit, but the bacterial load is high, so it has to be treated further. Maybe you have to boil the water, which is energy intensive, or add bleaching powder. The present work is deals with adsorption using alumina, and the other one is a long name, but I'll just call it resin later. Hybrid anion exchange resin embedded with zirconia nanoparticles. That we have not developed, but our collaborator Professor Arup has developed. So I'll call that resin. I'll explain what that is briefly. Then solar distillation, and if time permits, rainwater harvest. Here's the reverse osmosis plant at Yellampalli. This blue shed is the enclosure containing the unit. The treated water flows to an overhead tank and down to the collection tank. You can see villagers here collecting the water. So this operates a few hours a day. The problem with this unit, as I mentioned, is that the reject stream, which is discarded through a pipe into a drain, the reject water goes into a pond. So once again, it contaminates the water body. So here is the scale of the operation. In this case, the treated water is about 4 to 800 liters per hour, and the reject is 800 to 1200. So even more than the treated water. The hours of operation only 4 to 6 because electric supply is erratic in that village. Now, in this figure, what is plotted is the fluoride concentration versus days when we sample the water. Uh, this triangle is the treated water. You see, it is much less than 1 milligram per liter. So, it's acceptable and good quality as far as fluoride is concerned. But the feed is shown by the squares. You can see that it is above the acceptable limit, and it has to be treated. The reject water is shown by the circles, and that is even higher. The error bars are shown by these vertical lines. The error bars are large in some cases because we had to dilute the sample to measure the concentration. Here's the field level unit, spurred on by Arup's enthusiasm and confidence, because he had designed similar units for arsenic removal in West Bengal, Bangladesh, and Cambodia. The water from the reverse osmosis unit flows to an overhead tank and then is fed to a sand filter, and from there to the bed containing activated carbon, activated aluminum. Later, we wanted to use it for the resin, but we could not proceed for reasons I will explain. Here's the notation for the column experiments. Please remember only these things, that C0 is the inlet concentration of any ion, and Ce is the exit concentration. That is at the exit of the bed. The volume of the adsorbent bed is Vb, and the volume of treated water is V. So the ratio V by Vb is called the bed volumes in the literature, the convenient measure. The sizes of the pellets are of the order of 1 millimeter. reactions on alumina, in the when it's hydrated, the neutral form is this shown by ALOH. The three bars, horizontal bars, represent surface species. This is not in solution, but on the surface of the solid alumina. Activated alumina is alumina treated so that it has high surface area of the order of 200 meters squared per gram and is porous. So at the neutral species is predominates in the pH range 6 to 8 or 9. The pH is a measure of the hydrogen ion concentration, with high pH corresponding to low hydrogen ion concentration and vice versa. At low pH, the positive species predominates, AlOH2 plus, and at high pH, the negative species predominates. So at high pH, you may expect that this adsorbent won't work well here in this region. At low pH, it tends to bind the fluoride well. For resin also it's similar speciation. So the resin bead is like this. There's a polymer bead containing quaternary ammonium functional groups shown by this group here. The N plus nitrogen positive charge, that's a fixed ion. So the charge is balanced by mobile counter ions like chloride, fluoride, and so on, anions, negatively charged ions, which can move in and out of this bead. And in this bead, see, this bead doesn't really absorb much fluoride. The work is done by the dispersed zirconium oxide nanoparticles in the size range of 3 to 30 nanometers. They are dispersed in this bead using Arup's method. Now, if you these are the ones which have an affinity for fluoride, but not for other common ions such as chloride and sulfate, other negative ions. If you pack a bed with these nanoparticles, the resistance to flow of water will be very high. So to avoid this, we embed them in this bead which has much larger diameter and therefore much lower resistance to flow. Also, this adsorbent is much more robust than activated alumina, which you can crush with your fingers. It has low mechanical strength. The resin has another role because of this fixed charges. Let's look at this anion exchange resin on the right. Here R plus is a fixed charge, so it repels other cations such as calcium and magnesium from entering the beads and permits free exchange of negative ions such as chloride in place of fluoride and so on. So this is called the Donnan membrane principle. Donnan was a student of the legendary chemist Wilhelm Ostwald, just for historical information. Here is a defluoridation at the field level. On the y-axis we have plotted the exit concentration of any ion divided by the inlet concentration, and on the x-axis the bed volumes of water treated. I will explain why the data stops at around 80 bed volumes shortly. Let's go one by one. See, the fluoride inlet concentration is 2 milligrams per liter, which is above the permissible limit. But the treated water shown by the squares, black squares at the bottom, this is well below the permissible limit. On this scale, it will be about zero point 0.5. So we are doing fine as far as fluoride is concerned. But look at the chloride. Chloride is also okay, 699, which is within the range specified by the acceptable and permissible limits. But and the adsorbent removes some chloride and tends to level off. It's a typical behavior of a breakthrough curve. Now nitrate is a problem. The nitrate is nearly 10 times the permissible limit. So if it's 10 times the permissible limit, the corresponding value on the scale is 0.1, which is here. So only very few bed volumes of water can be treated, and most of the water coming out is not suitable for drinking. Actually, Kierkegaard said life has to be lived forward, but it can be understood only backwards. If only we had done lab experiments carefully, and measured all these ions coming out of the adsorbent bed, we would not have launched on this field level experiments. But anyway, one lives and learns. After 5 months, we found that there was corrosion at the wells of these columns and water was leaking out copiously. So we could not continue it directly. So the people who fabricated this columns said you seal the cracks with Bombay putty. However, we did not follow this suggestion because anyway the nitrate was not being treated. So we abandoned this plan. In between, I must tell you, we faced other difficulties. People were stealing pipe fittings because we were not there all the time. We did not have a watchman. We could not pay salary to somebody to look after it. So then we had to build an enclosure around the plant. We did that, but because of this problem, we could not proceed. Then after some time, we got reports that people were climbing up this structure and standing on top to view processions and other things. So then I got a nasty doubt. There's a government school just opposite. What if some child climbs up and tries to jump off? Then we will be in big trouble. So I'm very grateful to our mechanic, Mr. Mahadev Rao, who camped overnight and somehow got this dismantled. And so then the villagers refused to part with one of the tanks, but we were happy to let it go. Now, there's some work on the lab scale experiment, which is much more controlled. We have water flowing down from the top through an adsorbent bed sandwiched between beds of glass beads that are just to make the flow more uniform. And then you collect it in a tank. So ideally, each experiment should be repeated a few times, but somehow we did only once for each sample. And then, but you can see samples collected on different days do not differ much. The y-axis is the exit concentration of fluoride. That means at the exit of the bed here, divided by the inlet concentration there. Now the black one is the permissible limit for fluoride and is shown by this black dotted horizontal line. So up till about here, about 150 bed volumes can be treated. Similarly for the red, we have the red line. You can see here nitrate is well above the permissible limit of 1.5 milligram per liter, 45 milligram per liter, I'm sorry. This quantity adsorption capacity is often quoted in the papers. That is the mass of fluoride adsorbed per unit mass of adsorbent. See, this is very low compared to most studies, zero point 0.6, and that is because we are using RO reject, the reject stream. Very few papers deal with the reject water from an RO unit. And we will see that if you use synthetic samples, the value is much higher, maybe 5 times higher. My student prepared synthetic samples because he was getting tired of going to the field, which is 120 kilometers away, and bringing sample every time. So this synthetic reject water, which sort of mimics the RO reject, high concentration of nitrate and fluoride. Chloride is a bit high, but within the limits. And synthetic normal water, which has high concentration of nitrate and fluoride, others are in more or less acceptable limits. And then only fluoride water, SFW, which has fluoride, it has Na because we use sodium fluoride to prepare this sample. You can see if you go one by one, this blue circle, these purple circles, they're the synthetic reject water, and the breakthrough, which is see the concentration here, the fluoride is 5, so 1 by 5.2, that is the limit you should aim for. This is the concentration we should aim for, so we can treat about little over 400 milligram, 400 bed volumes. Then the next one is the synthetic uh, normal water. That shows a much higher value of the bed volumes. Surprisingly, the fluoride water is not to the right but in between these two. We believe this is because of the presence of some amount of bicarbonate in the synthetic normal water, which promotes the formation of positively charged surface alumina species, and this may bind to the fluoride. Okay, we'll see this reject water. This activated alumina perform much better than the resin for reject water. Here's the cost comparison for reject water. The cost is around 1 rupee per liter for alumina and 11 rupees for resin, which is unacceptable. For fluoride water, at the last row, the resin performs slightly better than the fluoride than the alumina. So this is some work on solar distillation. I'm coming to the end. Here the glass, there's the design of Thomas which we have used. Simple tray, inclined aluminum tray covered with a glass plate. The solar radiation passes through the plate and heats the water contained in a bed of sand. The water evaporates and condenses on the inner surface of the glass plate and flows down via gravity into a distillate channel. It's simple design, but not very efficient. Okay, this figure shows if you don't use the sand, you get much lower output. And even with sand, the reason is the sand permits the water to cover a larger area of the base. Even with sand, the output is lower than the figure quoted for good stills, which is order of 4 liters per square meter per day. Recent advances have pushed up this figure to maybe double the value. See here we can distill the RO reject water and get concentrations in the distillate which are much below the permissible limit, and so we can drink this water, and people have been drinking solar distilled water for a long time in some places. Okay, now I will summarize. I'll skip this rainwater harvesting. Prolonged ingestion of water having fluoride concentration greater than 1 milligram per liter can lead to fluorosis, and sometimes dietary interventions can alleviate the problems. Reject water from an RO unit at Yelampalli has high concentrations of these ions, and a lot of the feed is rejected. The alumina removes fluoride but not the other anions. The resin removes fluoride and to some extent nitrate but not really satisfactory. The cost of water has a wide range depending on the water treated, but none of these is commercially viable as of now. The reject water can be distilled using a solar still. However, there will be solid residue left behind in the still that will contain the fluoride and all that. So you have to figure out what to do. Some people have suggested we use it to make bricks, but this needs more careful and extended study to check whether fluoride leaches out from the bricks. Uh, okay, harvested rainwater is of good quality. After doing all this, sometimes you sympathize with Shankaracharya and like to say, it is hard to cross this ocean of fluorosis. Save me from it, merciful Lord. Thank you.
Sir, what is the correct value or correct level of TDS RO water? And does it mean that it has correct values of fluorine content and arsenic, if it is correct? Yeah.
Oh, sorry, I'm looking at
Yeah.
you want in the RO reject or the RO permeate? The
No,
treated water.
treated water.
Treated water TDS will be very low, well below the standard specification. So no problem with that. But it's sometimes RO treated water is supposed to be very soft. So in the domestic RO units, they add some minerals to the water.
Yes.
So that's the thing. Okay.
No, yeah,
You had some other question?
No. What is the correct level, sir, for RO? How much should be the TDS value?
See, there is no correct level, but more than about 1500 is not recommended. But 50 is a lower limit. Otherwise, the water is considered very soft. RO water is treated as very soft and you have to add something to it before
Yes.
drinking.
Okay. 100 or 150 is
Yeah,
okay.
yeah. All right. 100 and 150 is all right.
So it means that fluorine content will not be there if it is 100.
Yeah, fluoride is very less. No problem with the fluoride. Yeah?
Oh, okay. Thank you. Thank you, sir.
I just wanted to know. Hello.
Yes.
I just wanted to know. You said the solar distillation is like 4 liters per square meter, but is it over a day or?
Yeah, per day. I mentioned per day.
Okay.
4 liters per square meter per day.
Per day. Okay.
Per
so
day.
That's what I wanted. So it's a fairly slow process.
Yeah.
Okay.
Slow process.
Okay.
Yeah. Now we can get maybe 8 to 10 liters with some fancy designs. The cost will go up, the capital cost.
Hello. The figure you mentioned, the fluoride content in the water,
Yeah.
the acceptable limit of 1 milligram per liter.
Yeah.
How was it arrived?
Okay. The WHO.
Not forget WHO.
Yeah.
How is to be arrived here?
Okay.
We have a lot of faith in WHO. We are not questioning WHO.
Right.
How in India,
Yeah.
1 milligram per liter
Yeah.
fluoride content was arrived at?
Okay. I'm not sure exactly how they arrived at it, but this is what's specified in Indian standards, because fluoride is taken in from water and also food. So it is difficult to precisely tell what it is, but based on evidence, probably they must have said that one.
What kind of an evidence? If you take a normal Kaveri water,
Yes.
So let us say the Kaveri water in Sivasamudram area. What should be the fluoride content of the Kaveri water?
Kaveri water generally has below 1 milligram per liter.
How do we know?
We have tested water at IASc tap water.
Was it variable depending upon the season?
There will be variation, but we have not.
Is it variable?
Yeah, it's likely to be.
Has it been done?
No. At least we have not done.
How about water from Madikere to Sivasamudram?
No, I have not checked.
Nothing. Actually, the fluoride content in the water,
Right.
we just do it for publication's sake.
Yeah.
Okay. Really, what is the problem in India? How much of fluoride is there in any geographical terrain?
Yeah.
Each geography,
Yeah.
and therefore the bedrock geology,
Correct.
wherein we have the groundwater,
Yes.
is highly variable.
Yes, definitely.
There cannot be one value.
That's right.
This value of 1 milligram per liter is something which is highly questionable. Please work on that.
Yes.
How much are we having in any given terrain, and how is it variable?
Right.
Is something we should undertake.
Right, sir.
Please do that.
Right.
Thank you very much.
Thank you.
Can I ask a question?
Yes.
I just want to ask a very trivial question perhaps. These nanoparticles, you told us the size,
Right.
but they are embedded in some
Polymer.
So I wanted to know what is the size of the beads finally that one is.
The beads are order of 1 millimeter.
Okay. So they're quite a bit bigger.
Yeah.
Okay.
Okay, thank you very much for your wonderful talk. Actually, in Assam, we already surveyed some groundwater in our districts, and we got some lots of fluoride in our state.
Okay.
And is it possible to do some research in our area? Actually, there is no any such type of research for defluoridation of drinking water or like that.
Yeah, it is possible, but unfortunately, I'm not working on that problem now. Maybe many others. I can give you some names.
Okay, thank you.